Hi everyone, today we'll continue with the chapter applications of derivative, right? And today we'll be sketching polynomial graph using the tests and theorems that we discussed in the last lesson, alright? So before we start sketching the graph and before I talk about the procedure, let me revise something from the last lesson, alright? So whenever we sketch a graph, we need to know the graph behavior at each interval, right? Remember I mentioned about separating them into several pieces that are monotonic, alright? So if we take the first derivative, means we are looking for the slope of tangent line, alright? So if the slope of tangent line means the first derivative is positive, means the graph is increasing on that interval. If it is negative, means it is decreasing on that interval. And we already proved this using the Rolle's theorem and the mean value theorem in the last lesson, alright? So if it is equals to 0, means you have a horizontal tangent line at that point, means it is a possible critical, okay? And similarly, if f prime x is undefined, it can also be a possible critical. Usually this will happen to the rational function, alright? So we know that it is a critical point. How do we know whether they are maxima or minima? Then we have two options. The first one is the first derivative test. The test for local extrema. So for the first derivative test, we'll observe the sign before and after that critical point. Alright? So the sign of first derivative. If f prime x changes from positive to negative, means it was increasing then decreasing. The only way that it can happen is you have a local maxima at that critical point. Alright? If the first derivative changes from negative to positive, means it was decreasing and increasing, means you need a local minima. Alright? If the function is easy to differentiate, and you need to differentiate anyway because you need to find the concavity, alright? Then you can apply the second derivative test. For, I think I will combine concavity and this one local extrema together, okay? For concavity and also local extrema, okay? If the second derivative is greater than 0, means it is concave upwards. Alright? So in the interval which it concave upwards, and if you say that you give another condition, which is your f prime x is equals to 0, the only way that you can have a horizontal tangent line is at the local minima. Okay? Similarly, if your f double prime x is smaller than 0, means it is concave downwards. The only way that it can have a horizontal tangent line, okay, this one, tangent line, the slope is equal to 0, means it is a local maxima. Okay, so this is how you use derivative to find the behavior, whether they increase, decrease, the concavity, concave up, concave down, and to determine the local extrema for the graph. Okay? So with that in mind, now I will go through the procedure of graph sketching. Alright? Let me write the procedure for you. Okay? Graph sketching procedure. Okay, so what I mean by sketching polynomial graph means we need to know the general shape, we need to we need to plot a few important points, and we need to make it as precise as possible. If there are any asymptotes, then we also need to draw. Alright, so the first thing when we talk about graph sketching, the most important thing is the domain, okay, which is what you learn in the function chapter, right? So domain, because sometimes you have a y equals to square root of x plus 1, then you know that underneath this square root you cannot have negative value, alright? So you need to take note on the domain. If not, you will draw something that you are not supposed to draw, okay? Then this one is actually optional, which is the symmetries, if any, okay? And actually, the reason why this is optional is because this is just for you to check your answer and to make sure that you don't draw weird shape. Alright. So for symmetries, it's very easy to test. You just take f of negative x. Okay. So if f of negative x is negative fx, then you know that it is an odd function, right? Odd function. Odd function means what? Odd function means it is symmetrical about the line y equals to x. If f of negative x is equals to fx, then you know that it is an even function, means it is symmetrical about the y axis. Okay, but most of the graph that we will be sketching today, I think they are neither even or odd, so you can actually skip this step. Alright, then the step 2 is to find the possible criticals. Okay, and we are in calculus class, so the way that we find possible criticals is that we let the first derivative be 0, or I think I should use blue color to indicate this is the step that you need to do, equals to 0, or like I said, let it be undefined to find the critical points. And by letting it be 0 or undefined, we can solve for our x values. Then we sub into f of x, the original graph, to find the coordinate x, then fx. These are our possible critical points, f of x. Okay. Then since we already differentiate, then we can proceed with the piecewise monotonic intervals. Okay, piecewise. Okay, and we already found our possible critical points. So what we can do is we just simply draw a sign diagram for f prime x. What we do is actually, just draw a sign diagram. Let's say we have two possible critical points. Okay, possible critical 1, possible critical 2. Alright, then we just test for the behavior of f prime x at this interval, and this interval. Okay, so for example, if your possible critical 1 is 0 and you have another possible critical at 2, then maybe you just try to find the value. Actually, you don't need the value, you just find the sign of f prime, maybe simply a negative value, then f prime something in between 0 and 2, then this one something greater than 2, maybe a 4. Okay, then you go ahead and determine the sign, whether they are positive or negative. Okay, positive means it is increasing on this interval, positive increasing, then negative is decreasing. Okay, then you just determine the intervals which the graph is increasing. You just write increasing from negative infinity to 2 and decreasing from 2 to positive infinity. Okay, just determine the interval. And usually people don't write a closed interval because exactly on the possible critical points, the graph is neither increasing nor decreasing. It is a horizontal tangent line. Okay? Then now we are actually done with the first derivative. We will differentiate the second time. Okay? Which we will find, just now we find possible critical, now we find the inflection points. Inflection points. Okay? So it's very similar to our step 2. You just find the second derivative. Let it be 0 or undefined. Okay? Then we get the x values. Then substitute into our original fx. Then we get the coordinates of inflection points. Okay? Then since we already differentiate the second time, we can find the concavity at each interval. Okay? So we just draw sign diagram again. But this time, it is for the second derivative. Okay? So let's say you have inflection point, inflection point 1, then inflection point 2, or maybe another inflection point 3. Okay, you just go ahead and find, oh, this is positive, negative, positive, positive. Means concave up, concave down, concave up, concave up. Okay? Then with that, we can actually draw a combined sign diagram for first and second derivative. But this is actually optional. That's why I put in a bracket, because I will only recommend you to do this if your inflection points and possible critical points are totally different from each other. Okay? So that you don't confuse yourself when you sketch a graph. Okay? Then you just write a combined sign diagram. Okay, then you just draw a number line and then you label all the points, or maybe your inflection point 1 is here, your possible critical 1 is here, then your inflection point 2 is here, inflection point 3 is here, inflection point 3 is also your possible critical 1. Okay, then you just make them into a few partition. Okay, so from negative infinity to possible critical 2, there are both, this one should be possible critical 2, they are all increasing. Okay, increasing, then decreasing from possible critical 2 onwards. Then from this one, from negative infinity to inflection point 1 is concave up, then concave down. This one is still concave down, remember, because it is still in between inflection point 1 and inflection point 2. Then after inflection point 2 is on concave up. Then after that is also concave up. Okay. So until now, you can actually sketch a general shape of the graph already. But in order to make them more precise, you need to find the asymptotes. Asymptotes, if any, usually happen to rational functions. Okay, so like what we learned the limits chapter, limits and continuity. If we take limit when x approach infinity of the function and it equals to some values, means we have a horizontal asymptote. Okay, then if we take x approach some value a, you get positive or negative infinity, means we have a vertical asymptote. Okay, so sometimes you need to do long division because the graph may have oblique asymptote, parabolic asymptote and higher power asymptote, and any higher power asymptote lah, depending on the difference in degree of the numerator and denominator. Alright, so this is all the graph sketching procedure. Then of course the last step is to sketch the graph and plot important points. Okay, what I mean by important points, it includes the extrema and also the critical points. And of course you need to label your asymptote if any. And if possible, if it is very easy to find, you might as well also label your x-intercept and y-intercept. But this one is actually optional, up to you. Okay? Okay, now we'll look at the first example, which is an easy one. F of x equals to x to the 4th minus 4x cubed plus 10. Okay, so the first thing that you need to determine is the domain. And yeah, luckily this is not a rational function or anything crazy. So it is actually just from negative infinity to infinity. You can take any values. Okay, and this function is neither even nor odd. Okay, so there will be no symmetries. Okay, so the next thing that we need to find is the possible critical points. So we go ahead and differentiate. Okay, f prime x is, you bring down the power minus 1, bring down the power minus 1, you differentiate a constant, you get a 0. Okay, then in order to find the possible critical points, you need to let this f prime x be 0. So 4x cubed minus 12x squared is 0. Factor out x squared. 4x minus 12 is 0. X equals to 0. X equals to 3, right? By the principle of zero products. Then you substitute back into the function, this one. F of 0 and f of 3. F of 0 will just be 10. F of 3 will just be 81 minus 4 times 27, then plus 10. This should be negative 17. Okay, it will be negative 17. Okay, if you're not sure, then you just go ahead and press your calculator. Then the next thing that you need to do, before that, your possible criticals. You have 0, 10, and 3, negative 17. Okay, then the next thing that you need to do is your sign diagram for f prime x. Okay, since now you have two possible critical points, okay, I think I should use blue color. Okay, at 0 and at 3, they will just simply sub in any values. Maybe you try, where's our f prime x? F prime x is this one. You substitute in negative 1. Okay, 4 negative 1 cubed minus 12 negative 1 square, you get a negative 16. Okay, it's decreasing on this interval. Then what about in between 0 and 3? You just simply sub in maybe a 1. F prime 1 is a negative at, it's still negative. Then after 3, you just simply maybe sub in a 4, it is positive. Okay, so the graph will be decreasing, increasing. And if you like, you can write it is decreasing from negative infinity to 3 and increasing on 3 to positive infinity. Okay, then the next thing that you need to do is to find the second derivative. Okay, so again, bring down the power. I'm not sure if you can see. Okay, bring down the power minus 1, then bring down the power minus 1. Okay, then you try to, okay, by the way, this is your f double prime x. This is your f double prime x. You let f double prime x be 0. Oh, by the way, you should also let f double prime x be undefined if it is a rational function. But because for this one, I know that it is just an ordinary polynomial, so I actually skip this step. Okay, for rational function, you actually need to test for this one. Okay, so where will we? Yeah, this one. 12x squared minus 24x is equals to 0. Factor out 12x, x minus 2, x is 0, x is 2. Okay, then find your coordinates. Is 0, it was 10, right? 10, then f of 2 is, okay, we just type in calculator. 2 to the 4th minus 4 times 8 plus 10. It's negative 6, right? Negative 6. So you have two inflection points. 0, 10, and 2, negative 6. Then you draw your sign diagram for f double prime x. Now it is on 0. Okay, I think I should use blue color. It is 0 and what's that? 2. Okay. And where's our f prime? F double prime is this one. Okay. You substitute negative 1 into f double prime. 12 negative 1 squared minus 24 negative 1. You get a positive number, right? So it is concave up. You substitute a 1. You get a negative, means concave down. Then you substitute maybe a 6 into the equation. You get a positive number. Okay, means it is concave up, down, then up again. Okay, they will, if you like, you just write down the interval. Okay, concave up on negative infinity to 0 and from 2 to positive infinity. Concave down on 0 to 2. Okay, then the next thing that you might want to do is the combined sign diagram. Combined sign diagram, and I think I better use 2 colors for this. Okay, because we have possible criticals and also inflection points. Okay, 0, 2, and 3. Okay, 0, okay, and 3. This is your that one, right? Then 0, 2. Okay, so like this, and like this. Okay, so from 0, we look at the first derivative first. Yeah, from negative infinity to 3, they are all decreasing. Okay, decreasing. Then from 3 onwards, it is increasing. Then for concavity, from negative infinity to 0, it is concave up, then concave down, concave up, concave up. Then you combine 2 of them together. If it is decreasing and concave down, then the shape should be like this. Okay, the first half of a U shape. Then if it is decreasing and concave down, means you take the second part of the N shape. If it is decreasing and concave up, you take the first part of the U shape. My drawing is not so good lah, that one. Okay, then if it is increasing and concave up, you take the second half of the U shape. So with that, we actually found all the important points, and we also know the general shape of the graph. Okay, and for this graph, I don't think there is any asymptotes. Okay, I don't think there is any asymptotes. So there is no asymptote, means we can directly sketch graph. Okay. Okay, so the graph, you just label a few points. Okay, let me, is there any, yeah, should focus on, never mind, I just draw a normal one. Okay. Okay. So, I think we label all of our critical points. Okay, we have two critical points, which are 0, 10, and 3, negative 17. Okay. 0, 10, and 3, this is a 10, 1, 2, 3, negative 17. Not drawn to scale, of course. This is not drawn to scale. Then what about our inflection points? Is 0, 10, and 2, negative 6. So actually kind of overlap. 0, 10, this is also our inflection point, and 2, 6. 1, 2, negative 6. Okay, negative. Not drawn to scale, okay? Not drawn to scale. Then from negative infinity to 0, the shape is like this. The first part of the U shape, I'm referring to this one. Referring to this one. Then after that, it goes through an inflection point. It goes through an inflection point. Then this shape. Then after that, it is still decreasing, but concave up. Okay, but concave up. I think, okay, from here to here is concave down, yeah? Concave down, then concave up. Then after that is also concave up, but increasing. Okay, so it should be like this. But of course, my drawing is not so precise, and also not to scale. Okay. And this is actually concave downwards from here to here. It's not so nice. Okay, something like this. And I think this should be a little bit more smooth. Okay, then this one. Okay, yeah, nice. This is your y equals to x to the, where is it? X to the 4th minus 4x cubed plus 10. Okay, so this is your x-axis, this is your y-axis, this is your origin. Very nice. Okay? So what I want you to notice here is that just now when we are looking for a first derivative and we let it equals to 0, we say that 0, 10, which is this one, is a possible critical, right? But it happens that it is neither a local max nor a local min. It is an inflection point. That is why it is very important that we mention it is a possible critical at this steps. Okay, make sure you write it as possible criticals because it can be an inflection point as well. Similarly, okay, this case is still okay, but sometimes your inflection point, like I think I mentioned in the last lesson, if first derivative is equal to 0, second derivative is also equal to 0, it can be a local max, local min, or neither. Okay? So this is it for the first example, and the next one we'll be looking at a rational function. Okay, now we'll look at this second example. So for rational function, you need to make sure that you don't get any zero at the denominator, alright? So we'll proceed, we'll start with the domain. Okay, like I said, you can't have zero at the denominator, but in this case, I think we are safe because no matter what value you substitute into x squared, you will not get a negative 1, okay? So you are safe to say that the domain is from negative infinity to infinity. You need to draw the entire graph. Then what about symmetries? So you try to see what's your f negative x, and I think it is neither even nor odd, right? Because if you this one and x plus 1 square 1 plus negative x square, you get you expand this, okay, you expand the original one, you get plus here 1 plus x square, but if you expand this, you have a minus 2x here plus 1 plus x squared. Okay, so it is neither even nor odd. Neither even nor odd means it is neither symmetrical about y goes symmetrical about the origin, or it is also not symmetrical about the y-axis. Okay, then we can proceed to differentiate it, and I think we will need quotient rule. Alright, so I think it's up to you. You want to differentiate this one, also can. You want to expand, then differentiate, also can. But I think I will differentiate the original one because maybe we can cancel out something like that. Just need to use chain rule for that. Alright, so quotient rule, copy bottom, differentiate top. Okay, it's a chain rule, yeah. The inside is 1 plus copy, sorry, it's not plus, it's a minus, copy top, differentiate bottom square. Okay, then is there anything that we can factor? Oh, we don't have anything. Never mind, we just expand it. Okay, we try to expand. Oh, okay, I think, okay, the only thing that we can factor out maybe is a 2. Okay, then you just expand this one. You have x plus 1 plus x cubed plus x cubed, then plus x squared, minus, you already factor out the 2. Okay, you already factor out this one, then you expand this one, you get the x squared plus 2x plus 1. You multiply with x again, you increase every power by 1, x cubed, x squared, then plus x. Alright, close the bracket, then this one don't touch. Then time to cancel out stuff. X cubed and x cubed can cancel. X and x can cancel. So at the end of the day, you have 1 minus 2 is that. Okay. Oh, we can't cancel out anything. I think this is it. So the next step that we need to do is to find the possible critical. Let f prime x be 0, and because it is a rational function, we also let it be undefined. But I think we don't have any x value that will make the first derivative undefined, so don't worry. But I'm not sure about the second derivative, yeah. So what we have here, 1 minus x squared over 1 plus x squared equals to 0. So obviously, in order to make this 0, in order to make your left hand side 0, this part here have to be 0, right? Because you can't say that, oh, 2 times what will give you 0? 2 times 0 will give you 0. And over whatever is still 0. Okay, so just have 1 minus x squared is equals to 0. So who's your x? Your x is plus minus 1, right? Then for undefined, okay, yeah, we will not have any x value that will give us a denominator equals to 0. So we just ignore this part. But always make sure that you check first, okay? Then we just find out f of -1 and f of 1. What's our original function here? Okay, it's here, yeah? So -1 plus 1, okay, obviously we'll get a 0 for this. Then 2 squared is a 4 over 2, so it's a 2. Okay, hence we have possible criticals. Which are -1, 0 and 1, 2. Alright? Then the next step is to draw our sign diagram. Sign diagram for f prime x to determine the monotonic, the piecewise monotonic intervals. Okay, so you have two possible critical points. Okay, at -1 and 1. Okay, and then just test. Where's our f prime x? F prime x is this one, right? This one. Then you just simply substitute in any value that you like. Maybe I will substitute in -3. Okay, the values is not important as long as it is within the interval, then it should be fine. And the most important thing is the sign. Okay, so you have a negative value here. Then in between -1 and 1, I will just take 0. Just take 0. Is a positive. Is positive. Then I think this is, I will just take a 2. 1 minus 4, I think it's a negative. Yep, it's a negative. So it is decreasing, increasing, then decreasing. And if you like, you just write it is decreasing on, just now we said that the domain is -infinity to -1, right? To -1, and from 1 to positive infinity, increasing on -1 to 1. Okay, then the next step is to differentiate again, and I think let me copy the f prime x, because we need to do quotient rule again. Okay, 2 1 minus x squared over 1 plus x squared, right? Yep. Okay, quotient rule again. F double prime x. I think I just take out the 2. Take out all the constant multiples. Then you prepare this one. Okay. Copy bottom. Differentiate top. I already take out the 2, yeah? Then minus, copy top, differentiate bottom. Okay. 2x, am I right? I forgot something. Okay. 2, then 1 plus x squared, then inside function, chain rule. Okay. Now we have a lot of things to simplify here. But don't worry. I think this time we can factor out quite a lot of things, right? Okay, we can factor out 2x. And we can also factor out 1 plus x squared. Okay, if we factor out 2x, we still have a negative, yeah? This one we still have one factor here, then 2x, like that. I shouldn't have used red color for that. Okay, just for your information that we factor out this one, we factor out this one. No, we didn't factor out the negative. We factor out the 2x, we factor out 2x, and this one. Then this one becomes 3. Then we don't have to write this. Okay? Then negative 1 plus x squared. Then, yeah, I think you just 2 plus 2x squared. So it's a lot of algebra here. And I think, you know what? I just open this bracket. Minus x squared. Yeah, so that we can directly. Okay, this one multiply together. This is x squared minus 3 over 1 plus x squared 3. Am I right? Yup. I think we're right. So, to find the inflection point, we'll let the second derivative be 0. So again, we also need to let it be undefined. Oh, but it happens that we don't have answer for this again. Okay, because you always square your x at the bottom, so you'll not get a negative 1 anywhere. So I think I should use blue color for this. Minus 3 over 1 plus x squared cubed equals to 0. Okay, so 4x equals to 0 or x squared minus 3 equals to 0 by the principle of zero products. And again, we are multiplying both sides with 1 plus x squared cubed, yeah? So that we can get rid of this. 1 plus x squared cubed. Okay, we can get rid of this. And 0 times anything is still 0. Just to show you what we are doing here. And this one is the principle of zero products. Means if we have two factors multiplied together, it give you a 0. Means either one of them is 0 or both of them are 0. So obviously x equals to 0 and x equals to plus minus square root of 3. And this is not very nice because later on when we try to plot the inflection point, we need to like adjust the value a bit lah. Okay, and we know that square root of 3 is approximately 1.718 if not mistaken. I think 1.732. Sorry, my mistake. 1.732. Okay. Then yeah, the next step is f0. F0, it was, I think do we have that? No, we don't have. Okay. So we need to substitute back into this function here. Where were our original function? This one, right? Okay, I think I'll just do it here, like, cause I don't remember the function. Okay, so f of 0, f of square root of 3, and f of negative square root of 3. Right? We need these three values. So 0 plus 1 is 1 over 1, so it's 1. Then, okay, just rely on your calculator. 1 plus square root of 3 squared and then cancel out. Oh, you get a very ugly value, which is approximately 1.866. Am I doing it right? Because the values is not so nice. And obviously this will be the, okay, like this, yeah, approximately 0.13397. Okay, 1.866 and 0. Okay. So I will just directly write the inflection points, right? So inflection points is negative square root of 3, Then what was it? Where were we? 0.13397. Okay. 2 minus square root of 3 over 2, which is approximate negative 1.732 and 0.13397. Then we have 0, 1, am I right? 0, 1. And the last one is 1.866. 1.866. Okay. Set 3, 2 plus set 3 over 2, which is 1.732 and 1.866. Okay. That's the 3 over 2. Alright. Then the next one is sign diagram for the second derivative. Sign diagram for f prime x, f double prime x. Then just go ahead and draw negative set 3, 0, and set 3. Okay. Then where were we? Our f double prime x? It was this fella here, right? Okay, so I just take a negative 10. Okay. Then negative 10 square minus 3, 1 plus cube. It's a negative value here, so it's concave down. Okay, negative here. Then in between that one and that one, I just take negative 1. Is positive. Am I right? So it is concave upwards here. Then in between 0 and negative 3, I just take a 1, positive 1 I mean. Okay, then I think I will get a negative. Means it is concave downwards. Lastly, okay, I will take maybe a 2, because square root of 3 is 1.7 something, right? 2, I will get a positive, which means it is concave up. Okay, down, down, up, up. Then the next one is combined sign diagram, and I will recommend you to do this for this function because as you can see, the inflection points are totally different from the possible criticals. Alright, combined sign diagram. So you have negative square root of, I think I label the, what's that? Negative 1 and 1, okay? Negative 1, oops, sorry. Negative 1 and 1. So smaller than negative 1 somewhere here, negative square root of 3, in between is 0, square root of 3 is here. Okay, so smaller than negative 1 is decreasing, then increasing, decreasing. Decreasing, okay, I think I draw like this, I hope you can understand. Increasing, then decreasing. Okay, I think I better don't. This is so confusing. Decreasing, decreasing. You focus on the blue one, yeah? Increasing, increasing, and decreasing, decreasing. Okay? The blue one is what we got from our first derivative test for monotonic, piecewise monotonic intervals. Okay? Then the one in yellow is our second derivative test for concavity. Okay, concave down, concave up. Then in between 0 and square root of 3, down, down. After square root of 3 is up. Okay, so this is actually optional. It is down, okay, it is decreasing. Concave down means we'll take this part like this. concave, it is increasing concave up means it is like this. Increasing concave up means it continue like this. Am I right? No, this one decreasing. Sorry, decreasing means like this. So obviously you have a local, you may have a local minimum here. Okay, then after that is increasing concave down means you take this part. Then after that, decreasing, this one you take this part, means you have a local max here. And lastly, it is decreasing concave up means you take this part. Yeah. So now you generally have the shape of the graph. Okay, now it's time for asymptotes. This one sure got asymptotes one. Okay, so remember how we find asymptotes? Is using limits, right? And what was our original function again? Okay, let me write it here. Fx equals to x plus 1 square over 1 plus x squared. Okay, so now we test for which one should we test first? We test for vertical okay, we know that we don't have any vertical asymptotes, right? Because just now we already said that we don't have any x values that will give us a denominator equals to 0. Okay, so we will directly test for our horizontal asymptotes. And you know what? I think this graph, even though it has a horizontal asymptotes, but in the middle, you see in the middle, in the middle of the graph, I think the graph will cut through the horizontal asymptotes, you know. If you look at the values of those inflection points, those values of our critical points. Okay, I'm not sure about that, but I think it will cross through our horizontal asymptote. But anyway, okay, so when x goes to infinity, remember what we learned in the limits chapter? The degree on top is equals to the degree at the bottom. So now you refer to the constant attached to the highest power, and in this case it is 1 over 1. So we do have a horizontal asymptote at y equals to 1. Okay, horizontal asymptote at y equals to 1. Okay, and obviously, yeah, it will cut through our horizontal asymptote. Okay, anyway, is there any oblique asymptote or parabolic asymptotes? No, because the difference in power, the difference in the degree of numerator and denominator is 0. So we don't have that. We don't have oblique or parabolic asymptotes. Alright? And now we can finally sketch our graph. Let me get the axis first. But before that, oops, graph. Okay, let me get the axis so that it's easier for us to label later. I think this should be fine. Alright, so we will label the possible criticals: -1, 0, and 1, 2. -1, 0 means it is here. Okay, we have and just now we said that this is actually a local mean, right? -1, 0, and 1, 2. 1, 2, maybe somewhere here. And we said that this is a local maxima. Then next we label our inflection points: 0, 1, then okay, this one I think I need to refer because it is very small as well. Okay, 0, 1, I use yellow, yeah, for our inflection points. 0, 1 means it is here. 0, 1. Then somewhere, okay, negative 1.732, 0.3 should be somewhere here, right? This is our negative cert 3, and then we have, this should be 0.13397. 2 minus cert 3 over 2. And I think I better don't label it here, because later we will have our graph there. Okay. Then the next inflection point is 1.732 and 1.x66. 1.x66 should be somewhere here. Cert 3 should be somewhere here. Then this one 1.x66 should be somewhere here, right? Okay. And don't forget our asymptotes. Okay, asymptotes. And obviously, I think you can see already the graph will definitely cross the horizontal asymptotes. Okay, at y equals to 1. And I think I mentioned it right during our limits lesson. Okay, I said that it is possible that the graph, especially for a rational function, it is possible that the graph passes through our horizontal asymptotes. Okay, but horizontal asymptotes only means that when the x approach infinity, it will approach that particular values. Okay, and I think, okay, there is another thing that we actually forgot to test, and I tell you it is actually the same, negative infinity. Okay, to approach negative infinity, because you are squaring the power, right? You are squaring the x, so it is still equals to 1. Okay, so now what? Time to sketch. From negative infinity to negative cert 3, it is decreasing and concave downwards. Means this like this. But you see, you take note, from negative infinity, it will be smaller, it will be approaching, it will be here. Okay, it will approach the line y equals to equals to 1, because it is a horizontal asymptotes. Okay, so we just connect them to our first inflection point. Then after that, I think it is still decreasing. Okay, decreasing but concave up. Concave up now. Then after negative 1, it is still concave up but increasing. Okay. Concave up, then increasing. Then after 1, it is concave down but still increasing. Okay, it is concave down but increasing, and like this. After 1, 2, it is concave down, decreasing. And after cert 3, it is concave up and decreasing. But it will not touch our horizontal asymptotes. Okay. And this is our graph. Label it. Y equals to, what's that? X plus 1 squared over 1 plus x squared. X, y. And with that, we are done with this graph.